So in the last lecture, we discussed rotational kinematic motion, right, which is used to describe how objects rotate around an axis of rotation. So in this lecture, we were going to be looking at the rotational dynamics of our system. So this is like the part 2 to what we did yesterday. So we saw that rotational kinematic motion looked very similar to 1D kinematic motion. And you probably won't be surprised to know that rotational dynamics will look very much like the sequel to the kinematic motion lecture where we talked about forces, right? So the things that we're going to be talking about today are going to kind of look similar to what we did in week 2 of this course. But the point is, we need to explain why things rotate, much like we had to explain why things accelerate in certain situations. So we have a lot to cover in this lecture, so let's get to it. Now to begin with, I'll need to define torque. So we know that unbalanced net forces cause objects to accelerate, right? Newton's second law. And torques are the rotational analog that make things angularly accelerate. So we're going to define torque to be as follows. So the torque, this is a definition. We start by defining the torque on our system. There we go. And so the torque I'm going to define as tau, right? This is tau, not just t. And that's going to be equal to the magnitude of our force multiplied by this thing L here, which is the length of our lever arm. And I'll talk about that in a second. So the units of torque, right? It's units, right? We have a force multiplying a length. So it's a Newton, units of a Newton times a meter. So this thing on the left is what we call a torque. Here we go. So this is our torque acting on our object. This is the magnitude of the force producing the torque. So magnitude of force producing the torque. And then here L is what we call the lever arm. Lever arm. So when you push on a door to open it, right, you're not pushing on the hinges of the door because the hinges are the axis of rotation. That's what the door spins around, right? So you push some distance away from the hinges, usually on the doorknob or the end of the door, right? And the distance away from your axis of rotation that you're pushing, right, that distance is this L here, right? It's how far away the force is being applied from the axis of rotation. And don't worry, we're going to see a couple of examples and we'll get a little bit more familiar with it. So we also need to define the direction. So direction. So the torque is positive. The torque is positive. This is as much a definition as it is a convention. We could choose this any which way, but this is typically how we choose to define the torque. So the torque is positive when the force tends to produce a counterclockwise rotation about the axis. So I know it's a lot. So the torque is positive when the force tends to produce a counterclockwise rotation. Counterclockwise rotation about the axis. About the axis. All right, and when we talk about quote unquote the axis, we're talking about the axis of rotation. So comma, and negative when the force tends to produce a clockwise rotation. And negative when the force tends to produce a clockwise rotation. Right. So that's how we're going to define the direction. So let's look at some quick examples. This is going to be example 1. Example 1. All right, so example 1 says that a force with a magnitude of 50 newtons, a force with a magnitude of 50 newtons, is applied to a door. Is applied to a door. So find the torque. So find the torque if the lever arm is A, 1 meter. I'm going to go down like that, 1 meter. Or B is if the lever arm is half a meter. And then part C, if the lever arm is 0 meters, or that is, we're pushing on the hinges of the door. Right, that's the first problem. Okay, so let's look at part A. So what this is, we have our axis of rotation, let's call it this thing right here. And we have our door, right? And let's say that we're pushing on our door some force F, and then the distance from the axis of rotation to where we're applying our force. This whole distance right here is going to be our value of L. And this here is our force being applied. So for part A, L is going to be 1 meter. And so if we want to calculate the torque, well, that's not too bad. So the torque is just equal to the magnitude of this force, which we found to be, well, we didn't find it, but the problem told us it's 50 newtons. So 50 newtons of force being applied at a distance of 1 meter from our axis of rotation. This is going to give us a torque of 50 Newton meters. 50 Newton meters. That's our first answer. So part B, it's going to be basically the same thing. So the torque is just the magnitude of our force, but now it's being applied, half a meter away from our axis of rotation. So this is going to be 25 Newton meters of torque. And the last but not least, part C is asking, well, what if we're pushing at a distance of 0 meters from our axis of rotation? That is, we're pushing on the hinges of our door. So in this case, the torque that this force is applying to our door is the magnitude of the pushing force multiplied by the distance away from our axis of rotation. And this is going to be 0. So 0 torque is applied when we push on the hinges or the axis of rotation. That's part C. Right, so just like how unbalanced forces cause objects to accelerate, unbalanced torques cause objects to angularly accelerate. Right, a torque will cause an object to rotate. All right, so let's look at a little bit more complicated example. Right, this is going to be example 2. So example 2. So example 2 says, you are installing a new spark plug in your car. You are installing a new spark plug in your car. And the manual specifies, the car manual specifies that it be tightened to a torque, that it be tightened to a torque that has a magnitude of 45 Newton meters. So using the data in the drawing, and I'll draw that. So using the data in the drawing, right? Determine the magnitude F. Determine magnitude F of the force you must exert on the wrench. Of the force you must exert on the wrench. Okay. So like the problem says, there's a picture that goes along with this. So we have something like looks like this, and then we have, let's say this is our, like the bolt that we have to loose, or the nut that we have to loose. And so let's pretend like this is our wrench. There you go. And so let's say that we're applying a force F like this, right? And then the problem says that the distance between where we are applying the force on the wrench to the axis of rotation, which is the nut. So this distance here is our lever arm. And apparently this has a distance L of 0.28 meters. Right. So the question is asking, how hard do we need to push on this end of the wrench in order to apply a torque of 45 Newton meters to the bolt or the nut? Okay, so we know that the torque is given by 45 Newton meters, right? And we know that the lever arm is 0.28 meters. So using the fact that the torque is equal to the magnitude of the force multiplied by the lever arm length, right? We can solve this. We can solve this to find the magnitude of the force F. Right, that's just the magnitude of the torque divided by the length of the lever arm. This is 45 Newton meters divided by the length of the lever arm, which is 0.28 meters. So this gives us a magnitude of about 160.7 newtons. All right, so pretty straightforward stuff. So now that we're done with that, we must now amend our definition of a body that's in equilibrium, right? So if you guys remember, we said that an object was in equilibrium if there was no net acceleration acting on that object. So we now have to add in that an object in equilibrium must not experience any net torque acting on it. So this is going to be the section rigid objects in equilibrium. Rigid objects in equilibrium. All right, so the first couple of equations are going to seem similar, right? So we said that some of the forces in the x direction, right? If we're in equilibrium, then those have to add up to be 0. And same thing for the stuff in the y direction, right? When we add up all the y components for our forces, that has to be equal to 0 as well, since we don't want any net acceleration. But last but not least, when we add in all of the torques acting on our system, right, those also have to be 0. Units per Newton meters, right? Because we don't want our object to start spinning. Otherwise, we'd say it's not in equilibrium. Right? If it's not initially spinning, then we don't want it to spin. If it's already spinning, we don't want it to spin faster or slower. That's basically what we're trying to say here. So let's look at our third example. So it's important. Let me just highlight this. So our third example, example 3. Is about a woman on a diving board. So a woman whose weight is 530 newtons is poised at the right end of a diving board. Is poised at the right end of a diving board with a length of 3.9 meters. With a length of 3.9 meters. So the board has a negligible weight, so we'll pretend like the board is weightless. So the board has a negligible weight, and is bolted down at the left end, while being supported 1.4 meters away by a fulcrum. 1.4 meters away by a fulcrum. Right, which is just where this thing rotates around. So the problem wants us to find the forces F1 and F2. So find the forces F1 and F2 that the bolt and the fulcrum respectively exert on the board. So that the bolt and the fulcrum right, respectively. So F1 is the bolt and F2 is the force exerted by the fulcrum. Exert on the board. All right, so let me draw a picture. So here we have, the edge of our pool, kind of looks like that. And then we have, I'll try to draw this as best as I can. So we have a diving board, sort of looks like that. Right. And we have a bolt at the very end. I don't know how to draw any of this, so I apologize. There we go. That's the bolt. And we have like a fulcrum right here, just kind of looks like a little triangle. And then at the very end, we have a person, right, a woman, There we go. So the problem is saying that this distance here between the end of the diving board where the bolt is and the fulcrum here, this distance is 1.4 meters. And so we're trying to find the forces exerted on this diving board by this bolt and this fulcrum. So let me draw a free body diagram of this. So this is our diving board right here, right? Then at the very end, right here, right, the woman, her weight is pushing down. Right, she has a weight of 530 newtons. Like that. And then at the very left side, we have F1 of the bolt sort of keeping this thing down, right? Making sure the diving board itself doesn't fly off. So this is F1. And then the fulcrum is sort of in the middle here, like here, pushing up and making sure that this thing, you know, has something pushing up against it so it doesn't just fall into the pool. This is F2. Right. And so we're given some distances. So the distance between F1 and F2, at least where they're acting, this distance is 1.4 meters. And apparently the distance between the bolt and the woman at the end, this whole distance is 3.9 meters. Ooh. All right, so there's kind of a lot. So I'm going to take as my axis of rotation this left end bit over here. So this is going to be our axis of rotation for the purposes of this problem. So I haven't really talked about this, but when you're doing stuff like this, where you're working with torques, you're free to choose any point, you know, along here as your axis of rotation. But once you've chosen it, you need to stick with it throughout the entire duration of the problem. So to begin with, this is an equilibrium problem, right? We don't want this board floating up off into the atmosphere. We don't want it, you know, sitting down to the pool. We don't want it accelerating left to right, right? And we certainly don't want this board to start spinning, because then the woman would fall off or be launched backwards, so on and so forth. So we want the sum of the forces to be 0. So we want the sum of the forces in the x direction to be 0. But that's fine because all of our forces are acting in the y direction, so this part is basically useless. Right. And next up, we want all our forces in the y direction to be equal to 0. But we do have a lot of forces in the y direction. Right, so adding up all the forces in the y direction, we have the force F2 pointing upwards. I'm going to say that upwards is the positive y direction, right? And so the sum of the forces in the y direction are force F2 pointing up. We have the force F1 pointing down, so it gets a minus sign. And we also have the weight pointing down. So all that's equal to 0. And so for now, I'm going to box this off. Right, we're going to call this equation 1. And next up, we know that the sum of the torques in this problem need to add up to 0, right? Because this is an equilibrium problem. This is sort of the definition of an equilibrium problem. So we need to calculate the torques caused by all of these forces in our problem, right? So on the left, we have the sum of the torques. So we have F1. And so notice here that if we were to apply a force here, this thing wouldn't really rotate, but pretend like this axis of rotation was anywhere else, right? Then if we were to apply the force F1 at this point, this board would start rotating counterclockwise. So we'll say that this is positive. So this is going to be, the torque is going to be F1 times the lever arm distance, right? The distance away from the axis of rotation. But this force F1 is being applied directly to the axis of rotation. So it has a lever arm length of 0. Right, so that's gone. And now let's look at the force F2. Well, if this is our axis of rotation, right, pretend like these other forces don't exist. If it was just the force F2 acting on this diving board, right, this thing would make us go counterclockwise just like this. And so because of that, this torque is going to be positive. So this is going to be minus F2 times that lever arm length, right? The distance between our axis of rotation and where our force is acting. But in that case, that's just 1.4 meters. 4 meters. Right. And last but not least, we have the weight of the woman. So if the weight of the woman is the only force acting on this diving board, and if this is our axis of rotation, then this weight force is going to make this thing rotate clockwise. So this is going to be a negative torque. Let me actually move this down here so I have enough space to write. So since it's going to be negative, this is going to be minus the weight times the lever arm distance. Lever arm distance is just the distance away from our axis of rotation, which in this case is 3.9 meters. So all this is going to be equal to 0 Newton meters. And so as a little tip for when you're dealing with problems like this, if you have a bunch of forces and you're trying to figure out their magnitudes like we're doing here, a really good way to approach this is to first pick your axis of rotation to be on the place where that, like one of those forces is acting, right? Because you notice that when we're looking at the sum of torques here, this first one ends up dropping out, right? Because you're just multiplying by 0. The lever arm distance here is going to be 0. So as a result, this term falls out. And then we're left with F2, the magnitude of the force exerted by the fulcrum, times its lever arm distance of 1.4. Let's just assume that I'm going to divide by 1 meter on both sides to get rid of these pesky meters. So give me that minus the magnitude of the weight, just 530 newtons, I think. Yep, 530 newtons times that lever arm distance of 3.9 meters. It's going to be equal to 0. Right. So this is our equation 2. And you might look at equation 2 and think, well, the only thing we don't know about this is the magnitude F2. And you're exactly right. So what we're going to do from equation 2, we're going to solve equation 2 for the magnitude of the normal force exerted by the fulcrum on the diving board. Right, so we're trying to find the magnitude of F2. So from equation 2, right, we're going to solve. So we know that F2, right, the magnitude of that force, is equal to, right, if I add this to both sides, and then I divide both sides by 1.4, we get that this is equal to 530 newtons times 3.9 divided by 1.4. And so this tells us that the magnitude of the fulcrum pushing up on the diving board, right, F2, is equal to 1,476 newtons. Right, so that's one of our answers. There we go. And now that we know that, we can take this and plug it into our equation 1. So plug equation 1. And so this is going to tell us that F2, which is 1,476 newtons, right, minus F1 minus the weight, which is 530 newtons, is equal to 0. So if I add this to both sides, we get that F1, the magnitude of the bolt, keeping the diving board down, is going to be equal to 1,476 newtons minus 530 newtons for a total magnitude of 946 newtons. All right. F1 has a magnitude of 946 newtons. Right, and we got there by assuming that our system was in equilibrium and then working from there, right? We literally just used the definitions of equilibrium, right, where some of the forces had to be 0, and then the sum of our torques had to be 0, and then we worked from there. So again, the choice of the axis of rotation is completely arbitrary in our problems, right? Because if an object is in equilibrium, it's going to be in equilibrium with respect to any axis whatsoever, if that makes any sense. Let's look at the next example. This was example 3, I think. Yeah, so let's look at example 4. So example 4. So example 4 says, 2 blocks are placed at the ends of a horizontal massless board. 2 blocks are placed at the ends of a horizontal massless board. Horizontal massless board, right? This thing is massless because that's like one less thing we want to worry about. So the board is kept from rotating. The board is kept from rotating. Right? And rests on a support. And rests on a support that serves as an axis of rotation. It's an axis of rotation. So the mass of the first block is 10 kilograms. So the mass of the first block is 10 kilograms. So the problem wants us to find the mass. Find the mass of the other block. The other block. And the normal force exerted by the support. And the normal force exerted by the support. All right. So the corresponding picture, this thing kind of looks like this, where we've got our wooden board, and then we've got a support right here. This kind of serves as our axis of rotation, which I guess I can draw on a little purple circle. So axis of rotation is right there. Right, and there's 2 blocks. Block here. There's a block here, right, both at each end. So this one weighs 10 kilograms. And we're trying to find the mass of this block, as well as the normal force exerted by this, this support here in keeping this thing up. So we're trying to find the normal force exerted by this axis of rotation. All right. So for each of these boxes, we've got the weight, right? This is just M1G pulling down, and then one over here is just M2G, right? And so the problem gives us some last additional details so that the distance between the first block and our axis is going to be 1 meter. And then the distance between our axis and this second block, right, this is going to be 5 meters. So the second block's a little bit farther away. All right, so we're trying to find the normal force and the mass of the second block. So we're going to start by trying to find the mass of the second block. So this is our system in equilibrium, right? We don't want it to start accelerating upwards, downwards, left, right, and we certainly don't want it spinning. So what we're going to do, right? We're going to add up all the forces in the x direction. Again, there are no forces in this problem in the x direction, right? This is in the negative y direction, this is in the positive y direction, and this again is in the negative y direction, so there's no x components to any of our forces, so this is useless. We do not need it. But when we're looking at stuff in the y direction, this is not useless because we have 3 forces in the y direction, right? So we have the normal force pointing up, right? And we have the weight of the first block pulling down, and we also have the weight of the second block pulling down, and this should equal 0. So can't really do much more with this one. So we're going to box it off. I'm going to call this equation 1. And next up, we're going to look at the sum of the torques in this problem. So those have to equal 0 Newton meters. And so if this is our axis of rotation right here in the middle, right, if we're going to be adding up the torques, well, if we're looking strictly at the weight of the first box and how it's going to make this balance board, rotate, this is going to cause us to go counterclockwise around our axis of rotation. So this is going to be a positive torque. So it's going to be, right, the magnitude of this force, which is M1G, times the distance away we are from our axis of rotation, is 1 meter. Then we have the normal force, Fn, but this is at a distance of 0 meters away from our axis of rotation because it's pushing on our axis of rotation. So that's going to be 0. It's going to provide 0 torque. And then we have the weight of the second block, M2, right? If we pretend all these other forces don't exist, then this is going to make our balanced board rotate clockwise around this axis of rotation. And because of that, it's going to produce a negative torque. So it's going to be M2 times G, right? The mass, or excuse me, the magnitude of the weight for the second block times its distance away from our axis of rotation, which is going to be 5 meters. And all this should be equal to 0 Newton meters. Right? But this term is 0. So what we're left with is this term and this term, right? But the problem already tells us that the mass of the first block is 10 kilograms. So we know what this is. So in principle, we could calculate this. And so we can solve this equation for the mass of the second block, right? So we have, switch over colors. So we have the mass of the first block. So we have M1 times G times our distance, which is 1 meter. And on the other side, I guess I'll put that in. So 1 meter. Now on the other side, right, if I add this to both sides, we get M2 times G times 5 meters, right? But the G's cancel out because they're on both sides. And then if I divide both sides, by 5 meters, we get that the mass of the second block, in order to make this thing not rotate, right? The mass of the second block is just going to be equal to the mass of the first block divided by 5, right? Where I divided both sides by 5 and the units of meters would, get canceled out. So this is equal to 10 kilograms divided by 5 for a mass of 2 kilograms. All right, so the mass of the second block is 2 kilograms. Right? But now that we know that, we can take this newfound information and plug it in here, and we can use equation 1 to solve for the normal force of our support, right, pushing up on this board to make sure it doesn't fall down. Right? So I'm going to rewrite equation 1 here. Equation 1. So we have the normal force is equal to, now I'm going to bring both of these to the other side. So this is going to be m1 times g plus m2 times g, right? Where now I'm just factoring g out. So this is equal to m1, just 10 kilograms, plus m2, just 2 kilograms, times g, which is 9.8 meters per second squared. Right? So this gives us a normal force magnitude of 117.6 newtons. So that solves our problem. All right. So next I'd like to talk about something that we've been kind of glossing over ever since we even started looking at forces. So I'm going to talk about the center of gravity. So the center of gravity of an object. So center of gravity. Right? So every time we've solved the problem involving, the force of gravity, I've always placed the weight as originating at the center of the object. So that only works for highly symmetric objects like, I don't know, boxes, right? But most of the objects that we see in real life are not highly symmetric. So let's start by defining the center of gravity. You'll see why this is important. So the center of gravity, the center of gravity of a rigid body, a rigid body, right? That just means it's not squishy like a sponge. It's just, it's not going to deform as you move it. So the center of gravity of a rigid body is the point at which its weight can be considered to act when the torque due to the weight is being calculated. Due to the weight is being calculated. Right. And so this is defined as, first of all, the center of gravity is a position, right? It's the point in or around an object where you can basically put the entirety of the weight of the object there, right? So if the weight of an object is 1,000 newtons, right? If you're looking at a torque problem, you can consider the entirety of those 1,000 newtons to be acting at that point, the center of gravity. So the center of gravity is going to be x cg, right? Center of gravity. So it's going to be equal to the weight of the first, little bit of the object times its distance away from an axis of rotation, plus the weight of the second bit times its distance away from an axis of rotation, any axis of rotation, right? But once you pick an axis, you got to stick with it. So it's plus so on and so forth, right? Divided by all these weights. so on and so forth. So this is equal to the sum. You just add up all the like little bits of mass of the problem, and you multiply them by how far away from the axis of rotation you are. Then you just add up. And you just add up all these weights. So this thing right here is our center of gravity, and it's not as intimidating as it looks. All right, so let's look at a problem that deals with the center of gravity. So this is going to be example, what is this, 5? Example 5. So example 5. So example 5 says that the horizontal arm, like human arm, so the horizontal arm is composed of 3 parts. It is composed of 3 parts. So the upper arm, which the problem tells us has a weight W1, magnitude of 17 newtons. Right. The lower arm, which has a weight W2, magnitude of 11 newtons. Right. And the hand. Which has a weight W3 according to this problem, or a magnitude of the weight of 4.2 newtons. As a side note, if someone knows the exact weight of each part of the human arm, you should probably run. But luckily, we're doing this for physics, so it's not creepy, even though it's a little creepy. So the center of gravity of each part is shown. Center of gravity of each part is shown. All right, and I'll draw the picture after this. So find the location. Of the center of gravity. Center of gravity of the whole arm relative to the shoulder. Of the whole arm relative to the shoulder. All right. Okay, so I'm going to do my best to draw an arm. Please bear with me. So this is the upper arm. I guess maybe like this or something. This is the lower arm. I know this doesn't look like any sort of appendage you've probably ever seen before. So we got some hand with some big old cartoon fingers. So there's a hand. You know what? Actually not bad. Okay. So here is where W1 acts. Here's where W2 acts. Here is where W3 acts. So, right, this thing here is the upper arm. This thing right here is the lower arm. And then, to no one's surprise, this is the hand. Right, so W1 acts downwards like this. W2 acts downwards right here with magnitude of 11 newtons. W2 and W3 is the weight of the hand pushing downwards. So we need to know a little bit of information. So the distance between our shoulder and where, we can consider the weight of our upper arm to be acting, this distance here, is 0.13 meters. 0.13 meters. The distance between our shoulder and where the weight of our lower arm can be considered to be acting. Right, this is 0.38 meters. Last but not least, the distance between our hand, right, and our shoulder is 0.61 meters. And we're trying to find, the center of gravity for this arm. Okay. Well, we first write down, right, our center of gravity expression. So the center of gravity is just where the first force is acting times how far we are away from our axis of rotation, plus where the second force is acting, or how much the second force is times the distance away from the axis of rotation, plus the third force multiplied by how far away from our axis of rotation we are. And we're dividing by the weight or the magnitude of all these weights. Like that. All right, so this is it. So W1 has a magnitude of 17 newtons. So this is going to be 17 newtons times its distance away from the shoulder, which according to the problem is 0.13 meters. Right, plus the weight of the lower arm, which the problem tells us is 11 newtons, and that acts at a distance of 0.38 meters away from our shoulder, plus the weight of our hand, which is 4.2 newtons, and that acts at a distance of 0.61 meters. And all that's divided by just adding the weights together. So it's going to be 17 newtons plus 11 newtons plus 4.2 newtons. And so when you add all of this together, we get that the center of gravity for this particular arm is 0.28 meters. Right? Because the center of gravity is going to be a position. So, right, if this is 0.13 meters and this is 0.38 meters, then it looks like the center of gravity for our arm is going to be somewhere about like here-ish, maybe. This is our center of gravity for this arm. So that's that whole problem. So on this note, I'd like to talk to you guys about Newton's second law for rotational motion about a fixed axis. So basically, we're just slightly amending Newton's second law to now include, rotational stuff. So this is going to be Newton's second law. Newton's second law for rotational motion. Rotational motion about a fixed axis. There we go. All right. So the Newton's second law that we learned in the second week of this course, right, is the translational one. Translation, right, which, sort of equates to just sliding along in a particular direction. So this says that, the sum of the forces acting on our object. It's going to be equal to the mass of that object times that object's net acceleration, right? So this is the translational case for Newton's second law. But we can add in something for the rotational bits. Rotational motion. Motion. So for rotational motion, Newton's second law gets slightly amended as such. When you add up all of the torques acting on your object, that's going to be equal to the mass, or excuse me, the moment of inertia of your object times the angular acceleration of that object, right? So if you don't want your object to change its angular velocity, right? If you don't want it to, either start spinning, or if you don't want it to spin faster or slower, then you're going to want this angular acceleration to be 0. So here I is the moment of inertia, right? And this sort of functions as, quote unquote, the rotational mass for our system. So the larger the moment of inertia for our object, the harder it is to get it spinning if it's not already doing so. And then alpha, just like we saw last time, this is our angular acceleration. Angular acceleration. Right. Just like that. And so here, let me define the moment of inertia really quick. So moment of inertia, right? Like, how do we calculate it? Well, the moment of inertia is just going to be equal to the sum, right? You add up all of the different point particles of mass m, right? And you multiply that by how far away they are from the axis of rotation, right? So this is going to be in units. Units of, we have here units of mass, so that's going to be kilograms. Then we have here the units of distance squared, so the units of the moment of inertia are always going to be kilograms times meters squared. I could draw a better box than that. There we go. So that's how we calculate the moment of inertia. So let's look at an example. So I think this is going to be example 6, right? I think we've done example 5 previously. So example 6. So example 6 says that the motor in an electric saw, brings the circular blade, from rest, so from initially not spinning, up to the rated angular velocity. I don't know what that means, but up to the rated angular velocity of 80 revolutions per second. 80 revolutions per second in 240 revolutions. Right, so after this thing has rotated 240 times, this thing will then spin at 80 revolutions per second. So the problem goes on to say that one type of blade, has a moment of inertia has a moment of inertia of 1.41 times 10 to the negative 3 kilograms meters squared. So what net torque must the motor apply to the blade? Must the motor apply to the blade? Right. Okay. So we know that the net torque acting on an object, the net torque, is equal to the moment of inertia of that object multiplied by its angular acceleration. But the problem is we don't know what the angular acceleration of this thing is. So we need to figure that out. So the problem tells us that, after this thing spins around 240 times, we know its angular velocity. So the initial angular velocity of this thing is 0 radians per second, right? Because it's initially not spinning. And its final angular velocity is going to be 80 revolutions per second. But we need to convert this into radians per second, right? If we want to use any of our equations, we need to make sure that all this stuff is in radians and not revolutions. But we know that there are 2 pi radians for every 1 revolution. So the units of revolutions get canceled out. And then our final angular velocity is going to be 503 radians per second. So 503 radians per second. All right. So next, we know that the angular displacement of this thing is going to be 240 revolutions, right? It spins around 240 times, so the angular displacement is 240 revolutions. And just like we saw with the final angular velocity, we need to convert this from revolutions to radians if we want to use it in our equations. So this is going to be 2 pi radians in 1 revolution. The units of revolutions get canceled out, and we're left with an answer in units of radians. So this is going to be 1,508 radians. And with that, we have everything we need in order to calculate this angular acceleration. And then once we've done that, we can find the net torque that our circular saw motor has to apply to the blade. So what we can do is note that our final angular velocity squared minus our initial angular velocity squared is going to be equal to 2 times our angular acceleration times our angular displacement. Right? So right now, we're trying to figure out our angular acceleration. So what I can do, I can divide both sides of this, right, by 2 times our angular displacement. And when I do that, that'll give us our angular acceleration by itself. So we have that our angular acceleration is equal to our final, right, our final angular velocity squared. So that's 503 radians per second. We're going to square that minus our initial angular velocity squared. Well, that's just 0. So that's pretty easy. We're dividing that by 2 times our angular displacement, which we found to be 1,508 radians. Right. And so when you punch all that in, we get that this blade has to have an angular acceleration of 84 radians per second squared. Per second squared. And now we can finally figure out what the net torque has to be. Right? We just take the moment of inertia of our blade, multiply it by this angular acceleration, And that gives us the net torque acting on our blade. So the net torque acting on our blade is equal to the moment of inertia times our angular acceleration. Right? So the problem tells us that the moment of inertia for this blade is 1.41 times 10 to negative 3 kilogram meters squared times our angular acceleration of 84 radians per second squared, right? When you punch that in, you get a net torque. So you add up all the torques in the problem, and you get a result that says that all of these added together could be 0.118 Newton meters of net torque. And so that's the end of that problem. So really quickly, I want to go through and talk about rotational work. So the work done in getting something, up to speed. So rotational work. It's our next section. So rotational work. So the rotational work done when you've applied a torque tau to an object and you get an angular displacement of delta theta from that object. This is going to be the work done in making this thing spin. And maybe you'll notice some familiarity, right? Because when we were talking about the work done by a force F, right? The work done by a force F was just the magnitude of the force times the displacement times, cosine. So here, this is going to be the quote unquote magnitude of our force, right? And then here, this is going to be our, displacement, which we call D, right? So it's just torque times an angular displacement. And since this is work, this is going to have units of joules, right? So with rotational work comes rotational kinetic energy. So rotational kinetic energy, right? This is the kinetic energy attributed to something that it's rotating. So the typical kinetic energy that we talked about, in the, I think, last week's lectures, that kinetic energy is for translational motion, right? But now we're adding in the possibility that our object can rotate. And there's energy to be stored in a rotating object. So the kinetic energy of a rotating object, I'm going to denote by, Ke sub r for rotating kinetic energy. It's going to be equal to 1/2 times the moment of inertia of our object about its axis of rotation times its angular velocity squared. Right? And I keep saying this over and over and over again, but a lot of the stuff that we're going to see in today's chapter, or like all the stuff that we have seen in today's chapter, they have analogs with linear stuff. So just like how the linear kinetic energy was 1/2 mv squared, right? Now for rotational stuff, we have the rotational analog for the mass, which is the moment of inertia, and the rotational analog for our velocity, which is our angular velocity. So this is also going to have units of joules. Right? And now we get that the total mechanical energy for our systems, so the total mechanical energy right, whenever we're looking at a system, can now be rewritten like this. So the total mechanical energy is equal to its kinetic energy, 1/2 mv squared, plus its rotational kinetic energy, plus the gravitational potential energy, mgh. Right, so now we're adding in the possibility that our object can rotate. All right, so let's look at a quick example. This is going to be example 7, I think. So example 7 says that a 5 kilogram solid ball, a 5 kilogram solid ball, starts from rest, to roll down an inclined plane. To roll down an inclined plane. So find the velocity of the ball when it reaches the bottom. So find the velocity of the ball, or the magnitude of the velocity, I should say, when it reaches the bottom. When it reaches the bottom. All right. So the problem gives us a triangle. Kind of looks like this, right? This is our inclined plane. So the problem tells us that this angle here is 30 degrees. We have the ball up here at the top. Right, starting from rest. Apparently this is a height of 10 meters. And the problem tells us that the moment of inertia for this ball, right, is just 2/5 times the mass of the ball times the radius of the ball squared. Right, well, r is the radius of the ball. So let's capital R. All right, so we want to find the velocity of this thing at the very bottom. Okay, so the total energy initially is going to be the energy when the ball is up here, right at the top of the ramp, and I'm going to call the final energy when the ball is down here at the bottom of the ramp. So the initial energy of our system is equal to the initial kinetic energy, that would be now squared, right, plus our rotational kinetic energy, right, where I is 2/5 times the mass of the ball times the radius of the ball squared times our angular velocity squared. And then we have mg h naught, right? This is our last term is our gravitational potential energy. But the thing is, should be our initial angular velocity. The thing is, our ball starts from rest, right? It's initially not moving. And if it's not moving, it's not rotating. So this is also 0. And so the total energy of our system is initially just the gravitational potential energy of this thing at the top of the ramp. So we know that the mass of this thing is 5 kilograms. So the initial energy for our system is just mgh naught, or 5 kilograms times 9.8 meters per second squared, times the initial height of our ball. So it's going to be 10 meters, right? And this gives us an initial energy of 490 joules. We're going to keep track of that. And then next, if we're looking at the ball when it reaches the bottom of the ramp. So this is at the bottom of the ramp, right? It's going to be 1/2 times the mass times the final velocity of the ball squared, plus 1/2 times the moment of inertia of our ball, which is 2/5 m r squared times our final angular velocity squared plus our final gravitational potential energy. But at the bottom here, right, I'm going to say that this is a height of 0. And because of that, we're going to have no gravitational potential energy at the bottom of this ramp. Okay. Turns out that the total energy, so this is going to be 1/2 mv squared, right? The final kinetic energy plus, we have 1/2 times 2/5, which is going to be, right, the 2's cancel out, so this is going to be 1/5, but our mass is 5 kilograms, so it's going to be 5 kilograms divided by 5, so this is just going to be 1 times r squared. Right, I think that's why they chose this thing to be 5 kilograms, just so this kind of cancels out nicely, times omega squared. And that's going to be our final kinetic energy. Or excuse me, our final total energy. But since this ball is rolling without sliding, right, we're always going to assume that, unless otherwise stated. So because this thing is rolling without sliding, right, so if it's rolling without sliding, this means that the velocity at the bottom, right, the linear velocity, is equal to the radius of this ball times its angular velocity, right? So what we can do, we can take this and we can solve it for omega and then plug omega into there. Right? So according to this, we know that omega is just v over r. And we plug it into here. So then our final energy when the ball's at the bottom of the bottom ramp is 1/2 mv squared plus 1 times r squared times, where omega squared is just v over r squared. So this is going to be v squared divided by r squared. So the r's cancel out, r squareds cancel out. So then we're left with 1/2 mv squared plus v squared, right? And we can factor this out. So this is going to be, right, 1/2 times m, which is 5 kilograms, plus 1 kilogram times v squared, right? Where we're trying to find v. We're trying to find how fast this thing is going at the bottom. So this is going to be, right, so this is going to be 1/2 times 5, which is 2.5, plus 1. This gives us 3.5. So kilograms times our final velocity squared, right? That's going to be our total final energy, right? And if we use the conservation of energy, it says that our initial energy should be equal to our final energy. So on the left-hand side, we have 490 joules. And then on the right, we have final energy of 3.5 kilograms divided by v squared. So then I can divide both sides by 3.5. Right? So then we have the final speed squared of this ball at the bottom of the ramp is equal to 140 meters squared per second squared. And then if we take the square root of both sides, we can find that the speed of the ball at the bottom of the ramp, speed of the ball at the bottom of the ramp, is about 11.8 meters per second. Right? So interesting side note here. Because this ball has to start spinning as it goes down, right? It's not just sliding down, but because it's starting to spin, some of the total energy goes towards making this ball spin. If you were to repeat this same problem, except instead of a ball, you had a box that was sliding frictionlessly down this ramp, then you would find with the box, since it doesn't have to rotate, the box would end up going faster at the bottom of the ramp because it doesn't need to take any of its total energy and turn it into rotational kinetic energy. So in this case, the speed of the ball at the end was 11.8 meters per second. So that's all I've got for you guys today. If you have any questions, please let me know, but otherwise, I will see you guys tomorrow.